device which transfers the electrical energy from one circuit to the other circuit without the change of frequency. So the diagram of transformer is like this. So on one side we have the one winding, on the other side we have one more winding. Okay. So the winding at which we are going to connect the supply on source is called as the primary winding. Similarly, the winding at which you connect the load, okay, it is called as the secondary winding. So in the case of the transformer, what happens is whenever we give the supply to the primary winding, what happens? The primary winding there will be a flow of current I. So whenever this current I is flowing through the winding, so what happens is because of the right hand thumb rule, so around this winding you have the magnetic flux. Okay, so around that winding magnetic flux will be produced. Okay, so that flux by means of the core it travels to the other winding. Okay, the core is having basically two properties. One is the it's going to have low hysteresis loss, and high permeability. Right? So transformer core will have both two properties. So whenever it is having these two properties, it will allow the maximum flux to pass through it. Okay. Or you can say you can have here. Right. So what is happening? Now primary winding is produce the flux. Okay. So because of these two properties, high permeability property and we have reluctance also, low reluctance also. So whenever the transformers are having these two properties, what happens is the flux will be travel from the primary to the secondary without any loss. So whenever the flux travels to the core of the winding, so it comes and cuts the secondary winding. Okay. Whenever it comes and cuts the secondary winding, what happens is as per the Faraday's law of electromagnetic induction, so in the secondary winding there will be an EMF induced. There will be an EMF reduced, and that EMF is given by minus n into d phi by dt. Minus n into d phi by dt is the value of the EMF that is induced in the secondary winding. And here this n indicates the number of turns in the secondary turns, and the d phi by dt indicates the rate of change of flux linkages. So in this way, the electrical energy is transferred from this circuit to the other circuit without the change of frequency. Now coming to the classification of transformers, we can classify transformers into four types of shell type. And one more classification is based on the increasing of voltage or decreasing of voltage. So whenever I talk about increasing and decreasing, so it has been classified as step-up transformer as well as step-down transformer. Step-up transformer as well as step-down transformer. Like this we can classify. So coming to the step-up transformer. So when we can say a transformer is a step-up transformer. So we can say the transformer is step-up transformer whenever the secondary voltage is more than that of the primary voltage, we call the transformer as a step-up transformer. That means it increases the voltage. That's why we are calling it as a step-up transformer. Similarly, you can call the transformer as a second step-down transformer whenever the secondary voltage is less than that of the primary voltage. So like this, we can classify transformers based upon the increasing of voltage or decreasing of voltage. Now, we shall see the transformation ratio, which will relate the primary and secondary. The transformation ratio of the transformer is given by K is equal to V2 by V1 is equal to N2 by N1 is equal to, and it is I1 by I2. So this is called as the transformation ratio of the transformer. So therefore the transformation ratio, what we can do is we can relate the primary and secondary. So this is the transformation ratio. Next we will see the EMF equation of a transformer. What is meant by EMF equation of a transformer? So it is given by E is equal to is given by 4.44 Phi max F into N. 4.44 5 max F into M is the EMF equation of a transformer. So where it indicates the number of turns. So for example, if you are writing the EMF equation for the primary winding, is given by 4.44 5 max F into M. Similarly, if you are writing for the secondary winding, it is given by 4.44 5 max F into M. So like this, you can write down the EMF equation of the transformer. Now, while solving the problem, sometimes we will be given the fluxed state area of the code. Whenever we are given the fluxed state area of the code, we can write the EMF equation as E1 is equal to 4.44 Vm into A into F1 into N1. Similarly, E2 value we can write it as 4.44 Vmax A into F into, right? So this is the EMF equation of the transformer. Whenever we give the we are given the flux area of the core as well as flux density. So that is about the EMF equation of the transformer, by which you can find out the EMF that is induced in a particular point. Similarly, to go for the losses. So what are the losses? So when we are giving the input to the transformer, not all the input is transferred to the secondary. Some amount of power will be wasted as losses in the transformer. So what are the losses that are mainly occurring in the transformer means, first one is the core losses, and second one is the what you can say copper losses. So core losses and copper losses, these are the two losses generally that occur in the transformer. So core losses means these are the losses which are occurring in the core of the transformer. Okay? So these are the losses which are occurring in the core of the transformer. That's why we are calling it as a core losses. Similarly, copper losses, these are the losses which are occurring in the windings of the transformer, and these are that's why we are calling it as a